Super. So why don't I introduce Byron? It's great to have Byron back here, if only virtually, at Berkeley. Byron, a number of you know him already. He was an undergraduate at Prairie View A&M, which university, which I found out this morning by going on the web, is the second oldest university in Texas, and is this is its 150th anniversary. I don't know if you knew that, Byron. About the same age as Berkeley. After his time at Prairie View, he then went from there to the University of Minnesota, where he did his PhD, and then in surface science, and then came to the Advanced Light Source as a postdoc in X-ray science, working with Zahid Hussain. It turned out by phenomenal luck that just as he was finishing up his postdoc, I'd been here as chancellor for a year by then, and I'd realized I wasn't going to survive psychologically as chancellor if I didn't have a physics research program going on in parallel. And I managed to get some money from the Department of Energy, and I met Byron at an event, actually at the chancellor's residence, and we hit it off immediately. And anyway, Byron ended up joining me, and he basically established my research program here at Berkeley. And the timing worked very well because it was around that time, or shortly thereafter, that iron-based superconductors were discovered. So we got to do a number of foundational experiments together. So after his time with me, he then went from Berkeley to Argonne. And then from Argonne, he went to MIT, where he spent a number of years. Then he moved from MIT to the University of Louisville as a faculty member. And then more recently, both he and his wife, I guess they're both Texans, then decided to return to Texas, where they both took up faculty positions at the University of University of Houston, pardon me, in Houston. Byron, I should ask you, at the end, you can tell us about whether or not you have any power in your house, in your lab.
Okay.
But anyway, so Byron's contributed to a wide range of problems. Actually, one of the subjects that he worked on when we were collaborating, besides the iron-based superconductors, was phase transitions in liquid crystals, including looking at transitions from the nematic phase into the spectic phase. So he knew a lot about nematics in the context of liquid crystals. And that has recently emerged, nematicity has recently emerged as one of the important order parameters in high temperature superconductors, generally, and iron-based superconductors in particular. So Byron then jumped on this and has been carrying out beautiful research on this subject, both spin and charge nematicity, in fact. So today he's going to educate us all on what nematicity is, and specifically nematic fluctuations in iron-based Mott insulators. Byron.
Okay. All right, so thanks a lot, Bob, for the introduction, and thank you to everyone for the opportunity to talk and present the work. I'm assuming everybody can hear me okay? Yes, okay, I see some heads shaking. So yes, and so the storm, I'm surprisingly did not affect my home. So I got very lucky. I think everybody else I talked to had some either power outage or some bursted pipes. Amazingly, none of that happened to me. I don't know what happened, but okay.
Good.
Yeah. Okay, so let me talk about nematic fluctuations in iron-based insulators. I'm going to give somewhat of a general talk. I'll attempt to give a general talk that maybe helps to understand why we would want to look at Mott insulators within the context of thinking about iron-based superconductors. So I will give some introduction, as this is a colloquium. I know there are lots of folks here who already know some of these things, but nevertheless, I'll introduce iron-based superconductors, the high transition temperature superconductors. I'll talk about nematicity. And so my experiences with liquid crystals had me thinking a lot about the concept when it started bubbling up more and more within the business of iron-based superconductors. And so I would love to come and maybe give a talk that I've been doing work developing more ideas firmly within liquid crystals and talk about them, Bob, and put them to you very strongly within the context of iron-based. But so I won't say too much about liquid crystals today, but definitely my experience with Bob and doing liquid crystals and looking at nematic phase transitions had me thinking when this came up in iron-based materials. I'm going to describe electron correlation, and that's important for Mott insulators, and of course, high temperature superconductivity, but I'll put that in the context, electron correlation within the context of why we would want to depart from looking at the first type of iron-based superconductors, the more metallic superconductors like iron pnictides and iron arsenides, and instead take a look at iron-based Mott insulators. The particular iron-based Mott insulators that we will discuss are called the Oxychalcogenides. I'll describe them, and I will talk about a number of investigations that we've done on the iron oxychalcogenides to look at their structure, their electronic properties, and the magnetic behavior. Then I'll say something specifically about nematicity in those materials, and then try to put it within the context of the iron-based superconductors. So as many of you know, the iron-based superconductors discovered around or reported around 2008 have now grown to encompass a large range of materials or multiplicity of different compounds. And with the diversity of those compounds comes a diversity of structural arrangement, look, appearance, and transition temperatures. The figure on the upper left-hand corner is trying to show you some of the different forms of iron-based superconductors. And we come to kind of, in the parlance, refer to them as 1-1, 1-1-1, 1-2-2, or 1-1-1-1. And there are others, there are a number of others. What all of these compounds have in common is that there is an iron layer that is bonded to some arsenic atom or chalcogenide atom above and below the iron layer in an alternating fashion. So what you want to see in these four atomic models is that there's a commonality in the iron pnictide or iron chalcogenide layer. And that's given by the green and red, kind of almost tent-shaped like layers. Okay, these materials in general, a great many of the iron-based superconductors are fairly easy to grow. And they are also cleavable. The ease of growth has kind of helped to accelerate the study of these materials. And if you compare the growth of the iron-based materials to something like the copper oxide superconductors, the material handling and preparation is a lot easier. In addition to the ease of growth, there's the cleavable nature of the iron-based samples, which enables people to take the samples, put them into an experimental chamber, such as a vacuum chamber, then cleave quite easily the top surface to expose a relatively clean surface. The superconductivity is basically occurs in close proximity to some type of antiferromagnetically ordered phase. So in the iron-based superconductors, magnetism and superconductivity, as I will show, are closely positioned within the overall phase diagram of these materials. Okay, and also closely coupled to the antiferromagnetic phase will be something known as the nematic phase. Now, this nematic phase is essentially a C2 symmetry state in which the translational symmetry of the crystal is preserved, but its rotational symmetry is broken. Okay, most of the iron-based superconductors in the normal state have a tetragonal symmetry. And so that's a C4 symmetry. It's a fourfold symmetry. So if you go around the plane, the iron plane, by 90 degrees, you'll end up in a symmetric position at every 90-degree interval. Okay, the nematic phase actually breaks that fourfold symmetry and results in a twofold symmetry, such that if you go 180 degrees, let's say, around the plane, the iron plane, then you reach a symmetry equivalent position. So you have a twofold symmetry in the nematic state phase. Now the nematic phase, as I'll show you shortly, forms in between a structural phase transition and a magnetic phase transition. So in this talk, I'm indicating T sub S as the structural phase transition temperature and T sub N as the Néel temperature, or basically the magnetic phase transition temperature. Okay, so you can see a nematic phase forming in between these two very important temperatures. And that nematic phase not only manifests a crystal symmetry breaking, but it also manifests an anisotropy in the resistivity, if you take such a measurement. So there is an electronic nematicity that is associated with this structural nematic phase that forms, okay? And another important thing about the iron-based high TCs is the antiferromagnetism has a striped variety, meaning that there is a spin density wave or an anisotropic arrangement of magnetic moments within the plane of the iron layer along the A and B axes. So typically there's a double striped antiferromagnetic ordering within these materials. And finally, we have to note that the antiferromagnetism and the nematic order is thought to compete with superconductivity. Now, the phase diagram of a superconductor usually is drawn to kind of capture a lot of what we're understanding or we're trying to understand about a superconductor. And so what's shown on the upper right-hand corner is the phase diagram for a barium iron arsenide material. It's been doped with cobalt. This is a 122 material. And at the very top of the phase diagram at high temperature, that material is not superconducting. As you lower the temperature, the material undergoes a structural phase transition at TS, and then at lower temperatures, it undergoes a magnetic phase transition. And you see those phase boundaries labeled. In the non-superconducting phase or in the normal state, the crystal symmetry is tetragonal. As you lower the temperature, you enter an orthorhombic phase, and you start to enter a magnetically ordered phase, and that's the antiferromagnetism. Okay, so as you dope this material, and we're showing the doping along the horizontal axis, you can then drive down the structural phase transition temperature and the magnetic phase transition temperature. Okay, and importantly, the nematic phase that I was referring to is drawn in orange on this phase diagram. Okay, and that phase contains a symmetry breaking, structural symmetry breaking phase. Okay, now these fluctuations are, as we mentioned in the previous slide, can compete with superconductivity as well as maybe compete with antiferromagnetism. And you see that at the top of the superconducting dome, which is drawn in blue, that nematic phase is in close proximity to the superconducting region. One of the questions is on the origin of the nematic phase is important, and it's not yet answered. We'll bring this up a little bit later, but The exact origin, whether it's magnetic in nature, caused by spin fluctuations, or caused by some type of orbital fluctuations, is currently not, well, it's currently debated. All right, so these are some of the overall, this is a step back to discuss some very large characteristics of the iron arsenides. They're unconventional, as in the case of the cuprates and the heavy fermions, and that means that the nature of the superconducting pairing cannot really be explained by the BCS theory or the BCS coupling model of pairing, okay? Magnetism seems to play a very important role, as for reasons we just mentioned, and the role of magnetism, or the influence of magnetism, is also a hallmark of unconventional superconductivity. And another very important characteristic, a very broad and general characteristic of iron-based high TC materials, is that electron correlation is important. Now, let me say something about electron correlation, but let me say it in the modern parlance known as quantum materials. So these are materials that essentially, well, you might say all materials are quantum. Why do we need a term? Okay. Well, there is a term quantum materials basically indicates that you have a material in which there's moderate to strong electron correlation. Okay. And so one way to think about electron correlations is that there is an influence or an interaction between electrons that is at work and very important to the physics of the problem. You can think of quantum materials by comparing them to simple metals. In the case of a quantum material, the interaction energy will be greater than or equal to the kinetic energy that electrons have. So that means that that the perturbation theory that is used in band structure or band theory will not work in order to predict the let's say the conductivity behavior, or to understand the band structure of a quantum material. On the other hand, in the case of simple metals, the interaction energy between the electrons is much less than the kinetic energy of the electron. And so it's possible to use that in order to, with perturbation theory, of course, under the band structure model. So that's a colloquium level, I guess, way to distinguish between quantum materials and let's say simple metals. Of course, in quantum materials, you have to include the correlation, the electron correlation between the electrons in order to model the physics. And so quantum materials encompasses a broad range of different effects, and some of them I've listed here. I won't mention them explicitly. But quantum materials tend to have extremely complicated or quite complicated phase diagrams. And so here I'm showing the phase diagram for iron pnictides. I did show a previous version of this a few moments ago. Now this particular phase diagram is showing both hole and electron doping. And the diagram is meant to point out the evolution of the structure and the magnetism in the material as the iron pnictide is driven into the superconducting phase. So at high temperatures in the normal state, most of the iron-based superconductors are tetragonal. They are paramagnetic, so they have no magnetic ordering, and they are somewhat crappy or weak metals. So in the normal state, they're typically in a weakly metallic state. As the temperature is driven down, you undergo these phase transitions that I previously mentioned, and with doping, you can alter those phase transitions, drive those to lower temperature, and you can push the system into the superconducting state. And you'll notice these two secondary domes of superconductivity show, that give you a sense of the complication or the complexity of the phase diagrams. Now, there's the cuprate phase diagram, which is shown on the right, which has some general similarities to the iron pnictide phase diagram. And early on, as people started putting together the understanding the iron pnictides, they started asking the question, or they noticed the general similarities in the phase diagram and started asking questions about the similarities of the two types of material systems. One of those questions was that if you had cuprates that started out in the normal state as really strong insulators, and most of you will know they're copper oxide superconductors that are essentially ceramics, and they have a highly insulating character in the normal state. Okay, so the question was asked, are there some iron pnictides that might start out in the normal state as insulators? And then can we drive them into the superconducting phase? So this was an early question, as early as 2008, the year that superconductivity was reported in iron materials. And so that question of are there any iron-based superconductors that can start out as insulators and be driven into the superconducting phase is somewhat equivalent to the question that's at the top of your screen. Are the iron superconductors strongly correlated electron systems? Now, this is a historical question. So as I said, these were some early questions that were asked. This question at the top of the screen is better and better understood now. And so the short answer to this question is yes, they have some strong to moderate electron correlation. But early on, it wasn't quite clear. Now, the answer to that's the short answer. There's a number of complications within iron-based superconductors about the degree of correlation. Okay, for one thing, let me just say that it appears that for the iron bands in these superconductors can actually have varying degrees of electron correlation. So the D bands in the iron superconductors, some of them may be more itinerant than others. Some of them may be bound more in terms of their ability to conduct compared to other D band states. But early on, this was a question, and at the heart of that question was whether or not the Hubbard model could actually be used to describe the physics of iron-based superconductors. And in that model, there are two primary parameters: the Hubbard U, or the Coulombic interaction between electrons, and this T variable, which is usually symbolizes the kinetic energy integrals, or essentially the kinetic energy of a given electron. And so there's the term called the effective correlation, which is the ratio of the two terms. As that ratio increases above 1, you move into what's known as the strong coupling limit. And that indicates that you're dealing with a strongly correlated electron system, as opposed to an example of a weak coupling model in which you might have a spin fluctuations or some type of spin dynamics that influences the actual pairing, the actual electron pairing mechanism. All right, so this was an early question. And standing here in 2020, it's been answered better and better, although with lots of caveats and lots of places that you have to be careful. But early on, it was a prominent question from the get-go, but it still caught people by surprise when folks actually discovered an iron insulator that was really superconducting. And so this was a paper in 2011 from a collaborator. And so 3 years after the initial report, and this, I'm showing you this slide because it can give a very simple visualization of how an iron insulator is driven into the superconducting phase. And in this material, essentially creating iron vacancies actually drives the material more conductive. So here you'll see, for example, our good old iron chalcogenide plane here. And then the blue lattice is meant to represent iron plaquettes. Okay, so as you get to about 1.7 in the vacancies, and this is shown over on the phase diagram, you enter this superconducting phase. Okay, so this iron alkaline selenide is a nice insulator. There's no question, if you do an experiment and you measure bulk properties, no question this is an iron insulator. This is one of the first examples of where it was shown that you could actually take an iron insulator, drive it into the superconducting phase along the same lines or philosophy as you would a cuprate. So now I'm going to talk to you about a different type of iron insulator, one that's highly insulating. And this class of materials is known as the iron oxychalcogenides. And they essentially are a layered structure. You can think of them as a layered structure. If you move along the C-axis, you have different blocks. You have a perovskite block, and then you have a fluorite block. The bottom line is you end up with two different regions. This is, for those of you who know about the cuprates, this material is analogous to the rare earth oxide layer in a cuprate and the copper oxide layer. So it's almost like a charged reservoir and a conducting layer built in an alternating fashion along the C-axis. Okay, at the top of this figure, I'm circling with my mouse the actual iron chalcogen layer. All right, so I have a better slide of that here. And there are some important things to point out. So there's a similarity between these materials and the cuprate, as I just referenced, going back to the charged reservoir conducting layer. There is an iron chalcogen layer that's analogous to the iron pnictide layer. However, in these materials, in these iron oxychalcogenides, there is an oxygen layer here, and I think that color is pink. I'm a little colorblind, but there's an oxygen layer that sits in the center of the iron plaquettes. What this oxygen layer does is, so it's not quite the same iron layer as the pnictides. It has this oxygen layer in the center of the iron plaquette. What that does is it expands the iron unit cell. The effect of expanding the unit cell is really to increase the effective correlation that we mentioned back a few slides ago. And that leads you to a compound that is certainly more strongly correlated, okay, than the pnictides. And this is a strong Mott insulator, okay, to begin with. So at high temperatures, it has a tetragonal paramagnetic phase, as in the case of the pnictides. And this material was brought up a couple of years after the report of iron-based superconductivity as a candidate for an iron-based insulator that might be driven into superconductivity. And so I have a mistake on this slide because I have the sad face at the bottom bullet, but the sad face should also be at the bullet next to last. So it turns out after a lot of trying that these materials can't really be driven into the superconducting phase, okay? But, it turns out that they can only really be well made in powder form, okay? But because they have a close similarity to the pnictides, mainly that their level of electron correlation can be tweaked beyond that of the pnictides, they're interesting to study in terms of learning about materials that are close to the iron superconductors in the phase diagram, okay? So it turns out that the iron oxychalcogenides are actually, on the more insulating side of the pnictides in terms of the electronic phase diagram. So as a part of superconductivity, one of the main tools that we use, well, I shouldn't say that. I should say that we often use a tool of the approach of studying across the full electronic phase diagram in order to gain a better picture about what's going on with superconductivity. So I need to say something about models of electron correlation, because you'll see this. So I've been saying that the iron oxychalcogenides are Mott insulators, okay? And I've been talking about electron correlation. Let me say a few things, give a few more details. So the band structure theory, okay, for example, and models like local density approximation, they work, and if you think of a simple metal, they work well in describing those metals. And in that regime, the metallic state, there is no electron correlation in the band structure model. So the Coulombic energy U would be 0. If you want to take in more electron correlation and try to understand how electrons interact with their environment, you can apply the dynamical mean field theory model, okay? And that can be applied and has been applied, for example, when you have this non-zero electron correlation, okay? And so dynamical mean field theory will predict for you this kind of spectral weight. This is a density of states that emerges or gets changed as a result of adding more electron correlation. In the case of band structure and a simple metal, you have these blue states at the very top that represent field states. And then immediately above the field states, there are empty states. Those two are separated by some Fermi level, right? Adding some electron correlation will then alter the density of states, okay, such that you get the development of what's known as high energy spectral weight. And high energy meaning at energies higher than the Fermi energy, okay? So you get these shoulders in the spectral features. Okay, and so I think you can see it, but let me minimize. Okay, yes. So if the Coulomb energy becomes equivalent or on par with the kinetic energy term, then you start seeing the formation of what we call upper and lower Hubbard bands, okay? And then in the case of very, very strong insulators, if you will, then you can find something. Well, I should say that when you see these upper and lower Hubbard bands, these are forming due to the repulsion or the interaction between electrons, okay? You're putting some electrons farther away in the field states over here in blue, and you're putting density of states farther away. You're pushing the conduction band or the empty states farther away from those field states. And then in very strong insulating cases, you have these distinct occupied and unoccupied density of states that's on the order of, can be on the order of the Coulombic U value itself. So we can somewhat measure these well, I'm going to be careful here. We can assess electron correlation, okay, if we use tools that can detect this type of field state density of states and empty density of states. And there are a couple of ways to do that. Photo emission, for example, like angle resolved photo emission, can measure field density of states. These are electronic states. X-ray emission can measure a signal that is proportional to the field density of states, okay? And techniques like inverse photo emission or X-ray absorption can give you signals that are proportional to unoccupied density of states. Okay, so I'm going to now move this talk into experiments and some results. The first experiment I want to show you performed on the iron oxychalcogenides, right? These iron-based Mott insulators is a soft X-ray spectroscopy experiment performed at places like the ALS. And I will say only a few things about this slide, but I will say that for soft X-ray photons or soft X-rays, their energy is well matched to the transition metal edges, in particular transition metal absorption edges. And so soft X-rays have wavelengths of about 10 to 100 angstroms. That means that they have energies from like, 1 to maybe 1,000 electron volts, okay? Those energies can be tuned to the absorption edges of transition metals and oxygen for that matter, in order to excite electronic transitions, okay? And I'm going to show you that, an example of that in the next slide. So soft X-ray spectroscopy is a really good technique for measuring electronic density of states in materials like copper cuprates and iron-based superconductors. All right, so here's an example from ALS of one of the beam lines. It's a mess, as you can see. It's interesting to work with. It looks a mess, but it doesn't perform like, like a mess. It performs very well. What I want you to get from this slide is that this is an X-ray technique. It's called a photon in, photon out facility. And I will tell you what type of information we can get from iron-based superconductors as well as Mott insulators. So when you take a soft X-ray, for example, like the one given in blue on the left, and you tune it, let's say, to an oxygen 1s state, that energy, which should be around 530 electron volts, that energy will excite an electron out of the core state, the core oxygen 1s state, and can excite it into an unoccupied area, okay? That process is an X-ray absorption process. And it's possible to measure this signal, meaning the flow of the electrons out of the core level into the unoccupied state by connecting a drain current to your sample, okay? And collecting the current that is produced as a result of hitting it with the tuned soft X-rays. So it's possible to measure an X-ray absorption signature, okay? If you also measure the downward transition that occurs to fill this hole that you've created, you can detect the outgoing or the accompanying radiation, okay, in your experiment using the right type of detector. And that process of emitted radiation is known as, well, it's X-ray emission, but the technique is known as X-ray emission spectroscopy. So this figure is showing both how we do X-ray absorption spectroscopy and how we do X-ray emission spectroscopy. The plot to the right is meant to show you that the X-ray emission process will give you information about field density of states or occupied density of states in blue, whereas the X-ray absorption process would actually give you information about the conduction band. So in this case, this schematic is showing an oxygen X-ray spectroscopy experiment, oxygen X-ray emission experiment. Importantly, if you tune the incident photons to an exact absorption edge, then you can resonantly excite, okay, an X-ray emission process. And that resonant X-ray emission process not only has the ability to give you the density of a signal that's proportional to the density of states, a kind of a band structure, if you will. The resonant form can also give you excitations, because under the resonant condition, various electronic excitations have a higher probability of scattering or occurring, and that can possibly show up in your X-ray emission profile. So in the case of the iron oxychalcogenides, we can compare the iron-based superconductors, iron-based parent compounds, if you will, like the 111s, with one of our iron oxychalcogenides. And we see from this X-ray absorption measurement, okay, that the iron Mott insulator has a much narrower X-ray absorption band or conduction band, okay, compared to the iron pnictide parent compounds, okay? And so then we can also perform resonant enhanced X-ray emission, which is termed RIXS, at the L edge of our iron-based insulators. And we can tune our incident X-ray energies to different values, and those different values are shown vertically up the page. And some of these values actually represent absorption edges, okay? And what we can do is compare the resonant X-ray emission spectra that we get for our Mott insulator with that of iron-based superconductors. And so this figure actually shows that, but let me just talk about what you're seeing overall. This is resonant X-ray emission spectra that occurs as a result of tuning the incident X-rays to the iron L edge, okay? And the occupied density of state spectra that you get are shown on the page. And in particular, there are a few features to point out. The large mass that you see, for example, in the selenium version of the Mott insulator and the sulfur version of the Mott insulator, those large mass represent the main 3D iron band. Okay, and in some of the energies, energies that we use, for example, 707.4. Okay, these energies are close to the are taken close to the absorption edges. We see these extra features. Okay, these hump-like features. So these hump-like features are known as are examples of lower Hubbard bands. Okay, so these are features that show up because we are exciting electrons into the actual unoccupied density of states, and the downward transition is emitting X-ray photons that are from this this lower Hubbard band feature. Okay, so we do that, and we see that in both of our two different versions of the iron Mott insulators that we have. The selenium version on the left, the sulfur version on the right. Okay, so now what I'm showing you is the similar picture as before, but it's blown up. So we can see that we can compare iron metal RIXS spectra with that of an iron arsenide parent compound and one of our iron oxychalcogenide Mott insulators. And you see that in addition to the occupied density of states being narrow compared to iron metal and the iron pnictide, you see that there's this spectral feature that's about, close to 8 electron volts away from the Fermi level. So again, this main mass is the dominant portion of the iron 3D band. It's that type of high energy spectral weight also appears in the sulfur containing Mott insulator. All right. So one more RIXS spectra. Now we're going to show the oxygen K-edge RIXS taken on these two iron oxychalcogenides. And what they show essentially is that we collect RIXS spectra, and they're plotted vertically along the page, by exciting the samples at different incident energies of our soft X-rays. And you can see an evolution in this overall oxygen 2p density of states profile. And so what you gather is the overall presence of an upper Hubbard band in the oxygen 2p density of states profile for the selenium, and less so of the band in the sulfur containing compound. Okay. So let me go back. Are there any questions? Maybe I should, Zoom is kind of a tough business. Are there some burning questions right now?
Okay, apparently not. This is quite clear, Byron. So why don't you just keep going?
Okay, so, all right. So let me point out, let me just keep going and give a summary of, attempt to give a summary of some fairly complicated slides I just previously shown. So we performed iron and oxygen edge RIXS on these Mott insulators, okay? And I showed you that for the iron L-edge RIXS, we could see electron correlation in the form of this high energy spectral weight known as, which we characterize or we assign to Hubbard bands, right? This spectral weight comes about because of an excitonic process. You'll recall that that high energy spectral weight appeared at some incident photon energies, but not others. That's evidence that that spectral weight is excitonic in nature. If it's excitonic in nature, then it's related to the interaction between electrons. So this is why we say that it's a correlation-induced spectral weight, okay? Which is what you're going to see in an insulator, but you didn't see, for example, in iron metal, and you didn't really see clearly in the iron pnictide parent compound. In the oxygen edge RIXS, what we showed you was that you can actually go from the selenium to sulfur, and you can tune the spectral features a bit. Let me go back. So here at the oxygen edge RIXS, you'll notice that you have, this is RIXS, so this is occupied density of states. You'll notice that you have these high energy features in the sulfur compound here. These are Hubbard band features, but they don't exist in the selenium compound. And that lets you know that the sulfur compound is actually more of an insulating material than the selenium containing compound. So we can actually tune the Mott insulating behavior as we substitute from selenium to sulfur. Now, both of those atoms are isoelectronic, and the atomic radius of selenium is actually greater than sulfur. Our resistivity measurements, however, show us that the resistivity of the selenium compound is less than that of sulfur. Okay, so these resistivity measurements do not track, or they do not behave in the way that band theory suggests that they should on the basis of atomic radii. Okay, so all of this, so what we see between the iron RIXS and the oxygen RIXS is we see that there seems to be metallic behavior in the, there seems to be insulating behavior shown by the iron RIXS clearly, okay, where both Mott insulators have this correlation-induced high energy spectral weight. However, the oxygen RIXS shows a mixture that that one of the materials is less insulating than the other. So we have both metallic and insulating spectral behavior observed here. So all of that is consistent with this idea that there is some orbital selectivity to the Mott insulating nature of these materials, as people have observed across numerous iron-based superconductors as well. Okay. The other thing that these data show is that different D bands, okay, and then through their coupling with the oxygen, actually have more or less itinerant character. Okay, so there's some variety in the itinerant character of the D bands. Okay. So what I want to now do is show some magnetic data that we took on these materials. The magnetic data that we took used neutron diffraction, and we wanted to map out or understand the onset of the antiferromagnetism in these materials. And we wanted to see if we could understand whether or not the structure underwent a phase transition. So it turns out that these materials do not undergo a structural phase transition, but they do show a 2D Ising model behavior as they make this magnetic phase transition from a paramagnetic phase at room temperature down to an antiferromagnetic phase at lower temperature. In addition to that, we find that these insulators have a 2K or kind of a double striped antiferromagnetism in close similarity with a lot of the iron-based superconductors. And so in the lower right corner, we're attempting to show there's spin density waves along the that are orthogonal to each other that represent this this double stripe nature of the antiferromagnetism in these materials. Okay, so the absence of the structural phase transition, okay, and it made us ask or wonder, might there be something going on the short scale? So we didn't observe any structural phase transition with neutrons, or neither with X-rays either. Okay, and so the long-range ordering that occurs with a global change of crystal symmetry is absent in these materials. But we wondered if there might be still some type of changes in crystal symmetry on a small scale. So what we did was we used a technique that's known as pair distribution function. In this case, we applied neutrons, and pair distribution function enables you to understand the structural arrangement of materials on a local or small scale. And importantly, you don't have to have a single crystal sample. Pair distribution function can be used for the type of samples we had, which were, as I mentioned earlier, powder samples. Okay, so in pair distribution function analysis, what you want to have is a scattering as large a Q range or angular range of scattering that you can get, so that you can ultimately convert that scattering information, or what we call scattering vector information, into information about the small distances or the real space distances between atoms. In pair distribution function, you collect a broad range of both Bragg peaks and non-Bragg scattering in order to form a pair distribution function. And that is essentially a probability distribution for finding an atom at a given distance from some reference point. So if this works, you'll see as this plays, you'll notice that there is a match between the distance or the radii of the concentric rings from the center, okay? There is a certain probability of finding atomic density at a given radius. And the pair distribution function will give you a probability mapping for finding atoms at a given R or given radius. And that's what's shown here in the lower right corner. So we applied neutron pair distribution function analysis to our Mott insulators. And so with that, you can get numerous details. I said PDF or pair distribution function can give you atomic distances, okay? It can also tell you about lattice symmetry and lattice constants, of course. Okay, what we did was we took the A and B lattice information and we put that into an expression for the orthorhombicity, which tells you basically the deviation of A and B from each other. So in a tetragonal symmetry condition, A and B are the same. You expect to have no orthorhombicity. But as A and B begin to take on different values, then you should have a non-zero orthorhombicity. So we're calling that delta, and we're showing that. At the top, we have the pair distribution function. From this top figure, you're able to extract A and B parameters. Those A and B parameters go into the makeup of this orthorhombicity plot, which we're showing. The orthorhombicity is plotted actually as a function of R. And you can see that at small r's, at small distances, or shorter and shorter scales, the orthorhombicity takes on larger values. If you look over larger and larger scales, the orthorhombicity decreases, okay? So the PDF technique gives you some indication that on a short scale, there is orthorhombicity, or there's a breaking of the tetragonal symmetry. And so essentially you have some nematic ordering occurring on the short scale.
Byron, you should try and wrap up in about 5 minutes.
Okay, sure.
Okay.
So one of the things to note is that the paired distribution function gives you this short scale nematic ordering. That happens to be consistent with NMR data that we took also on these materials, where the NMR data showed this symmetry breaking from the high temperature, from the tetragonal phase with C4 symmetry to an orthorhombic phase, okay? And importantly, let me just say that on the larger scale, these materials have a tetragonal structure. So their long range ordering is still tetragonal, but on the short range, they have this orthorhombic ordering, okay? So NMR helps us to confirm that by indicating that, by showing that there's a slowing down of magnetic dynamics as we approach the Néel temperatures, which we're showing here, okay? Well, as you go farther and farther into high temperature. But as you approach the Néel temperature, which are these dashed vertical lines, the spin relaxation rate increases quite a bit, indicating that overall indicating that there's a critical slowing down as you go higher and higher in temperature away from the magnetic phase transition. That's indicative of nematic fluctuations. Okay, so let me make another point here. So this is another plot of the orthorhombicity, but this time we're separating the two Mott insulators, right? The sulfur containing compound at the top and the selenium compound at the bottom. And again, this is showing in the circular dot, in the circular marks, we're showing the orthorhombicity over a short scale, spatial scale, and the triangular marks show the orthorhombicity over a longer spatial scale or range. And so these show that the orthorhombicity that we're talking about is truly short range. All right. I'm almost finished. Let me just make a couple of comments, and I think I'll make them here. So the actual onset of the nematic fluctuations, okay, in this material, it turns out occurs over a fairly broad temperature scale. We actually see nematic fluctuations going, as I said, above the Néel temperature, and we see them or in the high temperature or the disordered regime, okay? And it turns out that people have observed nematic fluctuations also at high temperatures above the Néel temperature, above the structural phase transition temperature, as well as below. So for iron-based superconductors, these short-range nematic fluctuations appear to be, I have to be careful, but they've been observed in a number of superconductors now. And also we catch these things going on in these Mott insulators. In our case, we believe that the source of nematic fluctuations can be related to magnetism, okay? And that we think that the magnetism is actually a frustrated version, okay? So we think that the nematic fluctuations that occur in these particular Mott insulators is responsible for driving the nematic fluctuations that we see. We don't think it's necessarily orbital ordering. As I mentioned at the beginning of the talk, nematicity is in the field the origin is actually debated. But here in these materials, we think that the nematicity is driven by magnetism because it turns out that there's no ability to do an orbital ordering or orbital ordering cannot affect the nematicity because the relevant d bands or d orbitals are already separated in energy. Okay, so let me move on. So let me make some conclusions and I'll be done. So we've used a number of different techniques that we've applied to iron oxychalcogenides. And we've tried to address questions of electron correlation, magnetism, and nematicity. We've been able to show that these Mott insulators are bandwidth controlled, okay? They show orbital selectivity in the electronic behavior. We can actually tune the metallic nature. And we think that we're showing short-range nematic fluctuations, okay, that are magnetic, short-range nematic fluctuations of a structural type that are actually due to some magnetic influence, okay. I also want to make the point that The nematic fluctuations that we're observing here are also observed in other iron-based superconductors. Nematic fluctuations appear to be a general condition that's being found in actually more iron pnictides. All right, so I'm going to conclude my talk there.
Okay, thank you. That was terrific. Are there any questions? Just speak up.
So do you have any intuition for us why the phase diagram, when you showed for the iron-based superconductors upon doping, looked very symmetric on hole and electron doping versus, say, the cuprates, who are considerably more asymmetric?
Yes, so this is actually, this is actually an elderly phase diagram. So I think that actually they're not so symmetric. This is more cartoonish in nature. And Bob, I think I'm correct in saying that it's been found that the symmetry that's kind of suggested here is not actual.
Right, correct. And specifically on the hole dope side, phase diagram is much more elaborate. So it's really quite asymmetric with respect to the hole.
Right.
Right.
And so
this is historic for sort of teaching purposes.
Right. So this is a popular publication, but I should probably apologize for using this and not use this anymore.
I still use it too, but you're right. So Byron, have people found spin nematics in any other materials? Or is this the first one where there's strong evidence?
So I think the answer is that folks finding, that's a good question. In terms of iron-based superconductors, I don't think so. I don't think so. But however, the theorists are proposing that, spin nematicity can be one of, several other types of nematicity that would be at work or could be at work in materials like the iron selenide compound. Right. So I'm not sure that it's actually been discovered and identified, observed in an iron-based superconductor. But certainly it's been propagated by theorists as you know.
And what about the prospects for growing single crystals of these materials?
So, yeah, my collaborators have tried for a number, and I would say a number of times. They're very good, but the prospect is low because the materials seem to be, especially the sulfur-containing compound, they tend to be quite unstable. So there was one point where some people thought that they had grown materials in which they observed superconductivity, but it was always very hard for them to reproduce that measurement.
Okay. Any more questions? Okay, if not, let's just thank.
Well, I had my quick research before the talk. Nematicity seemed to be related to string formations, and maybe I have a wrong idea of that. But how do these get out of the unit cell, or how do they court other unit cells somehow?
Sure.
I imagine the string goes out of the unit cell.
Sure. So
is it magnetic?
So let me say this. So there are several. Well, I should say that nematicity is discussed confusingly in the advanced and forefront literature, even still, in my opinion.
Yeah.
But so what we usually mean when we say nematicity or the nematic phase is we're talking about a structural phase in which we have literally changed the crystal symmetry from something that's square-like to something that's more rectangular-like.
Okay.
In other words, we're going from a tetragonal symmetry to an orthorhombic symmetry. Now, if you imagine that a rectangle is longer in one dimension than it is the other, that can be described as nematic, meaning flowing or longer in one direction than the other.
Oh, okay.
Yeah,
it just goes from C4 to C2.
Right. But then there's also this idea of electronic nematicity, in which you measure differences in resistivities if you take the measurement along the A axis and the B axis.
Yeah. I must have seen that in the past.
Well, I would continue. Now, you probably did, but I believe that people don't write clearly about it. So
I know it's a problem. Yeah, of course, non-orthogonal resistivity is like, that's cool. It's been cool for a while. Thanks a lot. It's really a clear talk. You made it much more clear than most talks.
Okay, Byron. So thank you.
Okay.
And really happy that you actually kept your power in your water.
Yeah, me too.
Not trivial.
Well, hey, I'm going to tell you this. Oh,